Bismillahirrahmanirrahim. Hello, welcome to Math School. Today I'm going to give a short lecture on geometric progression. Uh, so this will be the first lecture on geometric progression. So let's start it better because we need to make a short video on this. All right, so I'm going to share my screen for this purpose. So all of you um, just uh, listen and just see the slides that I'm going to discuss. Hopefully, it will be really a good one for all of you. Okay, so here we go. All right, all right. The heading is geometric progression. In short, we call it GP. Today it's lecture one. All right, GP. The full name is geometric progression. It is a sequence, just like arithmetic progression that we discussed before, but it has a different characteristics. Okay. Here in GP, the numbers are consecutively coming with a constant, that means fixed ratio, when the post term is divided by the neighboring preceding term. It means when you are having a sequence like GP, then if you divide every post term by a just immediate preceding term, you will get a fixed result. I mean a ratio, and it happens in every consecutive numbers. For example, here we have an example. The numbers are like 9, 27, 81, 243, 729. Okay, let's see whether this is a GP or not. All right, so basically here, if we just see the terms, we see the first term is 9, then second term is 27, third term is 81, and then 243, fourth term, and fifth term 729. And here we see that if we think about 27, this is a post term with respect to 9, because 9 is its preceding term, just immediate preceding term. So if you divide 27 by 9, the result is 3. Then again, 81 and 27. 81 is a post term and 27 is a preceding term. So if you divide again to 81 by 27, the result is again 3. Similarly, 243 is a post term and its preceding term is 81. So here 243 by 81 is also 3. And so on. If we divide every post term here, we see that by its preceding term, the result is always 3. So that means this sequence is a GP because the result is always same. I mean the common ratio. We are getting a common ratio. So the constant result, the constant ratio, we can name it as a common ratio because it is happening every time. So it's a common incidence. That's why this ratio is called common ratio. All right. Mathematically, we can determine it as, the common ratio. Basically, it is denoted by R. So R is equal to post term by the preceding term. That means that I have discussed that every post term, if every post term is divided by its preceding term, and the result is always same, so we can name this ratio as common ratio, and it is basically denoted by R. And in example 1, just we have seen that the common ratio R was 27 by 9, or R equals to 81 by 27, or R equals to 243 by 80, or so on. So always it is coming same. That's why it is called common ratio. All right. So we have another example here, example 2, and the numbers are like 32, 16, 8, 4, 2, 1, half, 1/4, and so on. And in fact, here if we see, then we see the common ratio is actually half, because when you're dividing the post term by its preceding term, then the result is always half. Just like if you see that 16 by 32, the result is half, 8 by 16, the result is half, 4 by 8, the result is half, and so on. So this is a GP2 because this sequence is having a common ratio, which is half. So we can name it as the sequence as a common geometric progression. Or we can say it's a geometric series also. All right. Now the question is the common ratio. We see that in example 1, we have seen the common ratio was 3. And in example 2, the common ratio is half. And if you notice, the nature of common ratio in both the examples, we have seen that it has become, it is coming as a value which is more than 1, and also it is less than 1 in example 2. So that means when common ratio is more than 1, this GP is actually an ascending ordered sequence because the numbers are actually growing, increasing. And when R, the common ratio is less than 1, it is a descending order sequence. That means GP. So geometric progression will be just increasing when R is more than 1, and it will be decreasing gradually when R is less than 1. So this is very important thing that we should remember. All right. Now here again, just like arithmetic progression in other day, we discussed the notations. Here T1 means the first term, T2 means the second term, T3 means the third term in general. So we can name Tn as nth term. So n stands for any positive integer. I mean 1, 2, 3, 4, 5, and so on. So n can be any positive integer, which indicates actually the position of the term in geometric progression. Okay. Here we are actually going to discuss a formula which actually tells us about the general term. So this formula can find any term in a geometric progression. We are here using the red one. You can see the red writings. All right, Tn is equal to a r to the power n minus 1. So here Tn means, as just I told that Tn means nth term. So nth term is a into r to the power n minus 1. It means here a is first term, r is common ratio, and n is the position of the term. That means we can find any term, we call it here nth term, as a into r to the power n minus 1. And remember here r is common ratio, and common ratio is always found, always dividing by the second term t2 by first term T1, or T3 by T2, third term by second term, or T4 by T3, fourth term by third term, and so on. So that means always common ratio is found like this. So it is a very important relationship. That is, here you can just get this relation, and you can use this relation sometimes while solving problems. That is, T2 by T1 equals to T3 by T2, or equals to the T4 by T3, or equals to, and so on. So here, this is a very important relation which really helps us sometimes to solve many mathematical problems regarding geometric progression. By the way, here, so nth term is a into r to the power n minus 1, and remember a is first term of the geometric progression, and r is common ratio, n is the position. Okay. So here, if we see example 1 again, if we want to find 8th term, we can denote it as T8. And here A is, since A is first term, which is 9, R is common ratio 3. So if we plug in this value in this formula, Tn A into R to the power n minus 1, then we can write as T8 is equal to 9 into 3 to the power 8 minus 1. So it is giving us the 8th term, which is 9 times 3 to the power 7. And we can simplify this by using calculator. All right, so this is just an application of the formula. Okay, now the other formula, here the formula comes to find the summation of geometric progression. Okay, if you want to get the sum of a certain number of terms in a geometric progression, then we have to just use basically two types formula here. The formula actually is chosen considering the value of r. If r is more than 1, look at the red writings. If r is more than 1, then formula would be like this. Sn is equal to a into r to the power n minus 1 by r minus 1. And here, if r is less than 1, I mean common ratio is less than 1, then formula would be like this. Sn is equal to a into 1 minus r to the power n by 1 minus r. Remember, here a is first term as usual, r is the common ratio, and n is the number of terms. So if you see that since you are using a, I mean first term, that means you are getting the summation of first n terms, starting from the first term till the nth term. If you add up all the terms in a geometric progression, what will be the result? That can be determined by this formula. But remember, when you are going to use this formula, first see what is the value of r. If it is more than 1, choose the right one, right formula, the red one here, and here if r is less than 1, the other formula. Okay, this is very important to remember. Okay, and here a means the first term that we have just discussed, n means the number of terms that we want to add up, and r means the common ratio, Sn means the sum of the first n terms. Okay, that means you remember you are actually adding up first n term. That means starting from the first term till the nth term. That means first term, second term, third term, fourth term up to nth term. You are adding up all of them. Okay, so here is application of the formula. The sequence, the example one is here again. A is 9. First term, R common ratio is 3 and is 8 because we want to add up 8 terms of this sequence. I mean of this series. So S8, that means summation of first 8 terms. That means starting from 9, the first term, then plus 27, plus 81, and so on. So just plugging, and you have to choose the right formula because R is 3 here, so it's more than 1. So you know which formula is to be used here. So this is the formula. So if you're plugging all this value, so the result is here 29,520. That means first term, second term, third term, fourth term, and lastly the 8th term. If you add all of them, okay, the result would be what? 29,520. So this is the use of the formula to find the summation. Okay, so why this formula nth term was like this, that is Tn is equal to a into r to the power n minus 1. So if you look at the terms like in the series is ar squared, ar cubed, ar to the power 4. It means a is first term, ar is second term, r squared is third term, and so on. So we can say that T1 is first term, which is a. We can say that there is nothing with a, that means 1. So 1 can be written as r to the power 0. That means common ratio is there with a 0 power. So we can design it like a r to the power n minus 1. 1 minus 1. Similarly, T2, second term AR, which is with a common ratio R with power 1. So 1, we can design it AR to the power 2 minus 1. Similarly, T3 AR squared, which can be written as AR to the power 3 minus 1. T4, similarly, AR cubed AR to the power 4 minus 1. So if you notice, then what happens here? Look, T1 AR to the power 1 minus 1. T2 AR to the power 2 minus 1. T3 AR to the power 3 minus 1. T4 AR to the power 4 minus 1. So have you noticed one thing? That is here A is always there, constant. R is also there, and the power of R is -1, -1, -1, -1 is always there. But the change is 1, 2, 3, 4. along with the position of the terms 1, 2, 3, 4. So they have relationship. That means position and the subtraction of the, you know, R's power from 4 is like that. So here Tn Tn is AR to the power n minus 1. Okay, so mm, all right. So now we are again we are going to start our lecture. Again, there was an interruption. Sorry for that. All right. So here we go again. So thing is here the term nth term is again AR to the power n minus 1. That means here position of the term is n and power of R is always, remember, from the position there would be a subtraction 1. So AR to the power n minus 1. So this is the pattern and thus we get this. Now why the summation of this series AR to the power n minus 1 by R minus 1 when R is more than 1 or the other formula. So actually, you know, Sn means, as I told you before, that actually we are going to add up the terms starting from the first term. So A plus AR squared, AR cubed, AR to the power 4, lastly AR to the power n minus 1. So that means starting from first term till nth term, we are going to add up. So we are naming it as Sn. So if you, and naming it as equation 1. So if you multiply uh, equation 1 by R, we get another series, AR to the ARSN equals to AR squared, AR cubed. Actually, R is being multiplied with every term, so we get this type of relation. So this is, we are naming it as 2. Now, if R is more than 1, what will happen? RSN and SN have, you know, that inequality. That means if R is more than 1, obviously RSN is more than SN. That means this, see, equation 2 has a, is bigger by value than equation 1. That means we can separate equation 1 from equation 2. So if you go do that, then by subtraction, if you see that equation 2 is here at the top, then underneath that equation 1 we are writing and we are subtracting equation 1 from 2. So the sign is changing. So as a result, RSN minus SN, here AR is cancelled out, AR squared is cancelled out, AR cubed cancelled out, AR to the 4, AR to the 5 would be cancelled out. Similarly, AR to the power n minus 1 would be cancelled out by the term just before the previous term of AR to the power n here. There is a term here. So this would be cancelled out with this. So ultimately what is remaining? What do we get here? AR to the power n and here negative A. So this is the thing that we are ultimately getting because rest of the numbers are being cancelled out. So RSN minus SN is equal to AR to the power n minus A. That means this is the thing ultimately. So if we take SN common here and A common here, we ultimately get this. This is the algebraic part. So you should understand. And it is when R is more than 1. So similarly, if R is less than 1, so same thing, but RSN would be less than SN. That in that case, we will just subtract equation 2 from equation 1. So same thing will happen, just cancelled out. Cancellation would be almost same way, but A and here negative ARN will be remaining. So from that, we will just achieve this formula where R is more than less than 1. And that's all about the slides. So I hope you understood. So I think, and there is a worksheet I have given um, in your Google class. So if you just see the lecture again, and the lecture was also is uploaded. So just see the lecture again and start the worksheet, because the worksheet is also solved. So if you have any problem, I will come online. I will come on live again, and you can ask me your questions. Okay. Thank you very much for listening to me. All right.